Hey everyone, and welcome to today's Explainer. Have you ever stopped for a second to think about the fact that your entire visual world is being run by this invisible, silent geometry playing out all around you? I mean, seriously, every single time you look in a mirror, throw on your glasses, or even just stare at a glass of water, you are witnessing the absolute unbreakable laws of physics happening in real time. It's wild. So today, we're going to unpack the fascinating reality of how light reflection and refraction actually work in our daily lives, and we'll map out the hidden science that dictates literally every visual interaction we have. Okay, let's dive right into this by starting exactly where most of us start our day, standing in front of the bathroom mirror. You raise your right hand to brush your teeth, but the reflection staring back at you raises its left hand. So why does that happen? Well, it's a neat little phenomenon known as lateral inversion or left-right reversal. But to truly understand why your mirror self is a flipped copy, we've kind of got to look at the very basic mechanics of bouncing light.
Section 1. The Morning Routine. Plane Mirrors.
So, the fundamental law of reflection dictates that when a ray of light strikes a smooth, polished surface, like your bathroom mirror, it bounces back. And it follows a very strict rule to do this. The angle at which the light hits the mirror is exactly equal to the angle at which it reflects. Think of it like a perfectly thrown tennis ball bouncing off a wall. But here's the catch. Because of how those light rays bounce back to your eyes, your brain actually gets tricked into seeing what we call a virtual image. The light rays are bouncing off the glass, sure, but your brain traces those rays backward, creating this apparent intersection of light behind the wall. The image isn't actually real, meaning you couldn't put a projection screen behind the mirror and capture it. But the geometry is so unbelievably precise that this virtual image appears to be the exact same size as you, standing at the exact same distance behind the glass as you are in front of it. Section 2. The commute. Spherical mirrors. All right, so you leave the house and jump in your car. We're officially leaving flat mirrors behind and entering the world of spherical mirrors. These are reflective surfaces that literally form a small piece of a larger imaginary sphere. And as you'll see, adding a curve changes the rules of the game entirely. For instance, if you used a makeup or shaving mirror this morning, you used a concave mirror. Its surface curves inward, kind of like a bowl. When you get up close to a concave mirror, it creates a virtual, erect, and highly enlarged image, which is absolutely perfect for seeing small details. But look at your rear view or side mirrors in the car. Those are convex mirrors. They curve outward. We rely on convex mirrors in traffic because no matter how far away the cars behind you are, a convex mirror will always form an upright image while giving you a much, much wider field of view.
Now, what's really interesting here is how scientists map this all out. To predict how these curved mirrors warp our reflection, we have to look at their hidden anatomy. There are a few key anchor points. First, there's the pole, which is the exact center of the mirror's surface. Then there's the center of curvature. Since these mirrors are basically slices of a sphere, this point is the dead center of that imaginary sphere. Connecting those two is a straight line called the principal axis. And finally, you have the principal focus, this magical little point where parallel light rays perfectly meet up after bouncing off a concave mirror. Using that specific anatomy, light has to follow some unbreakable, universal traffic laws, which lets us draw really precise ray diagrams. Step 1. Any light ray traveling parallel to the principal axis will always reflect through the focus. Step 2 is the exact opposite. A ray passing through the focus will always reflect out parallel. And step 3, a ray traveling directly through that center of curvature, it'll just hit the mirror and retrace its exact path right backwards. By tracking just those 3 paths, you can predict exactly where an image is going to appear.
Section 3. The math behind the mirror. So the crucial point is figuring out how we actually calculate these distances without our brains hurting. Physicists rely on what are called Cartesian sign conventions. Just think of the mirror's center as the 0 point on a graph. Anything to the left of the mirror, where the object actually sits, is a negative distance. Anything to the right, sitting behind the mirror, is positive. Anything pointing up is positive, and anything pointing down, like an inverted image, is negative. It's a beautifully simple system that keeps the math perfectly consistent. And with those rules in place, we arrive at this gorgeous fundamental equation, the mirror formula. 1 over v plus 1 over u equals 1 over f. In this formula, v is the distance of the image, u is the distance of the object, and f is the focal length of the mirror. This single equation universally connects the object, the image, and the mirror's specific curvature all together. And hey, if you want to know exactly how big that image is actually going to be, you calculate the magnification. It's just the ratio of the image's height to the object's real height. But elegantly, you can also calculate it just using the distances we just talked about. It's simply a ratio, negative v divided by u. If your result is negative, you know mathematically for sure that the image is real and upside down. If it's positive, the image is virtual and upright. The numbers literally tell you the whole story.
Section 4. The lunch break. Bending light.
Okay, imagine you're at lunch and you're looking at a straw sitting in a glass of water. Notice how it kind of looks broken right at the waterline? Or maybe there's a slice of lemon inside that looks massively magnified compared to its actual size. Well, in this case, light is no longer just bouncing, it's bending. And that introduces us to refraction. When a ray of light passes at an angle from one transparent medium, say the air, into another, like water or glass, its traveling speed actually changes. And because it changes speed, it changes direction. It bends. If it enters a denser medium like water, it slows down and bends toward the normal line. So just how fast are we talking here?
Well, in a vacuum, light travels at a staggering 300 million meters per second. That is literally the universal speed limit. It travels just a tiny bit slower than that in the everyday air around us. But the second those light rays hit the water in your glass, or the glass itself, that massive speed reduces considerably, physically forcing the light to pivot.
And this brilliantly illustrates how we measure that slowdown using something called the refractive index. It's basically a ratio comparing the speed of light in a vacuum to the speed of light in a specific material. The higher the number, the slower the light travels, and the more it bends. Water has an index of about 1.33. But get this, look at a diamond. It has a massive refractive index of 2.42. Light absolutely crawls through a diamond, bouncing and bending drastically inside it, which is exactly why diamonds sparkle so intensely.
Now, just like reflection, refraction follows strict rules too. The second law of refraction, famously known as Snell's law, states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant for any given pair of materials. Basically, this means the universe mathematically locks in exactly how much that light is going to bend before it even touches the water.
Section 5. Afternoon reading. Lenses that shape vision.
So later in the day when it's time to read and you put on your eyeglasses, you're literally harnessing refraction. Eyeglasses are nothing more than carefully engineered, transparent, spherical lenses designed to bend light into our eyes perfectly. And there are two main types of lenses that do this. A convex lens is thicker in the middle and thinner at the edges. It's a converging lens, meaning it takes parallel rays of light and bends them inward so they all meet nicely at a single focal point. Conversely, a concave lens is thinner in the center and thicker at the edges. It's a diverging lens. It takes light and spreads it out, making the rays look like they're emerging from a virtual focal point hidden away in a cave, so to speak. Let's see how this builds on our earlier math, because lenses behave a bit differently than mirrors, meaning the lens formula is slightly tweaked. It's 1 over v minus 1 over u equals 1 over f. And the magnification formula also flips its sign. It's simply a positive ratio of v to u. The math just adapts perfectly to whether light is bouncing off a surface or passing straight through it. We'll conclude our technical journey with how an optometrist actually writes your prescription. The power of a lens is simply a measure of its ability to bend light, and it's calculated as 1 divided by the focal length. We measure this in a unit called diopters. Because convex lenses converge light, they have positive power. Because concave lenses diverge light, they have negative power. So if your glasses prescription has a minus sign of it, you are literally wearing diverging concave lenses right now. That is exactly what that number means.
Which brings us to the end of our daily journey. Seriously, take a look at your immediate surroundings right now. The screen you're looking at, the reflections in the room, the glasses on your face, or the glass of water sitting on your desk. How many billions of invisible rays of light did you just bounce and bend with perfect mathematical precision just to watch this explainer? The physics of reflection and refraction isn't just something stuck in a textbook. It's the silent geometry that builds the world you see every single second of your life. So what else is hiding in plain sight? Keep looking closely at the world around you, and I'll catch you in the next one.